Welcome everyone to today's Berkeley Nucleonics series of webinars. Today's webinar will focus on vector signal generators and their role in radar simulations. We're here to give you a better understanding of vector signal generators as well as their significance in the field of radar simulations. A vector signal generator, also known as a vector signal source, is a piece of electronic test equipment that is used to generate signals for various applications. It is commonly used in the field of radar simulations as it provides a realistic simulation environment that can be used to test, evaluate, verify, and optimize the performance of radar systems. Radar simulations play a critical role in the design and development of radar systems. They provide a safe, controlled environment in which engineers can test and evaluate the performance of radar systems without the need for expensive hardware or equipment. This helps to ensure that the radar system is functioning correctly and any issues are identified and resolved before the system is deployed. A vector signal generator provides a realistic simulation environment by generating the necessary signals to simulate the radar system's performance. This includes generating signals that simulate the radar signal's frequency, phase, and amplitude. Phase noise, switching speeds, and modulation capabilities are the most important things when you are selecting a vector signal generator for radar applications. With the rapid advances in technology, radar systems are becoming more complex and sophisticated, making it increasingly difficult to test their performance using traditional methods. Vector signal generators provide a solution to this problem as they allow engineers to generate realistic signals that simulate the radar system's performance under a wide range of conditions. We will be discussing various aspects of vector signal generators and their role in radar simulations. We will start by providing an overview of vector signal generators, including their basic functions and key features. This will include the ability to generate signals and precise frequency, phase, and amplitude, as well as the ability to generate signals in real time and in a controlled environment. Next, we will touch on some of the different types of radar simulations, such as full-scale simulations, laboratory simulations, and hardware-in-the-loop simulations. Each of these types of simulations serve a unique purpose and provides different benefits. After that, we will examine the importance of vector signal generators and radar simulations, including the benefits they provide and how they help to ensure the accuracy of the simulations by providing realistic signals that simulate the performance and characteristics of the radar system. The ability to perform these tests and to identify and resolve any issues before the system is deployed in the real world save time, money, and potentially lives. We will also discuss the various types of vector signal generators that are available and their specific functions and capabilities. Vector signal generators come in a variety of forms, including standalone units, integrated systems, and software-based solutions. Each type of vector signal generator has its own unique features and capabilities, and we will discuss the pros and cons of each type in detail. Finally, we will take a look at the vector signal generator, or the future of the vector signal generators and radar simulations, including emerging technologies and trends in the field. So if you're an engineer, researcher, or just curious about this topic, then this webinar is for you. Get ready to learn about vector signal generators and their role in radar simulations. So let's get started. My name's John Reynolds. I'm a Vice President of Berkeley Nucleonics, and my colleague here, Edgar Guzman, is a Solutions Engineer. This is a webcast overview. We won't go through that. All right, so BNC and RF microwave solutions. Berkeley Nucleonics is located in Cedar Fall, California, where for over 50 years we've been servicing customers and providing the highest quality and industry-leading technology and unparalleled products, service, and support. All of our RF and microwave signal sources and phase noise test systems are 100% made in Switzerland with Swiss parts by our partner Anapico of Switzerland. If you are interested in any of our RF microwave signal sources or vector signal generators or phase noise test systems, this slide right here goes over our BNC service regions. In the East Coast, we have ATM and Brennan. In the Midwest, we have Base 8. In the Southwest, we have PMR. The states in between Texas and California are covered directly by BNC. In Northern California, we have Rankin and Associates. In Southern California, we have Ace Tech. In Mexico, we have Mexer. And in Canada, we have Stratitech. If you are outside of the Americas and you're interested in any of these products, our partner Anapico of Switzerland can help you directly. Please contact them at sales@anapico.com, and they are able to call or quote and help you with any application requirements. Anybody in the Americas, you could reach us directly. Contact information will be in the last slide. I will pass the baton to my colleague Edgar Guzman, and he will start the introduction to vector signal generators.
Hi, thanks, John. So as John said, I'm Edgar Guzman, one of the engineers here at Berkeley Nucleonics, and I look forward to going over, a little bit of what the vector signal generator can do, especially in terms of radar simulation. So a vector signal generator, as you can see from the images here, it's essentially a RF signal generator that creates vectors in the IQ field, and you can see the IQ graph here. So you have vectors, obviously. You have a magnitude and phase, which is identified there. Our particular vector signal generator is a digital vector signal generator. So you can see the image all the way on the right. It shows the I and Q signals coming in and being mixed with our quadrature LO signal. And quadrature just means we have two signals, usually sine waves, one at a 0 phase and the other one at 90 phase. So they're in quadrature with each other. So we take our two IQ signals, or the one IQ and the one I and the one Q signal. We take them, we mix them together in a combiner. And then that goes through a digital analog converter, and then from their point, it's upscaled and then output through our RF circuitry. So the main feature of the vector signal generators is it can do the IQ modulations. That's how you generate a majority of your signals, and you can mimic or duplicate a lot of different modulations, AM, FM, phase, using IQ modulation. And there's also, with the benefits, there's less intermodulation, and you can't see it on this actual picture here, but the I and Q signals are coming from digital filtering. So whether that be a band pass or low pass filter, that's filtering out the unneeded frequencies of your signal. So the main features of a vector signal generator, or pretty much any RF or microwave signal generator, usually boils down to frequency range accuracy, the amplitude or the power level which you're capable of outputting, and even the accuracy of that. The phase noise of the actual signal, as well as the switching speeds. So depending on the application, all of these may be critical to you. Some of them may be critical, and you may only need the frequency, may only be the thing that you're interested in. In radar simulation, it tends to be majority of these are fairly you need to have fairly precise specifications in most of these specifications here. So how does the VSG work? So a VSG, essentially, it makes your IQ signal, and as you saw from the previous slide, it mixes them together and gives you your signal output. So if you need to do a phase modulation, you can use IQ signals by having a quadrature pair. And then as you change, say you have a sine and a cosine, that's a quadrature pair. If you change the amplitude of your cosine, the phase of your signal will shift. Because it's adding them together. So you have two sine wave pulses, and when one gets larger, it's shifting the combine towards that way. And if you do the sine, it'll shift the other way. So that's how you can mimic a lot of the, or actually create a lot of the analog modulations using IQ modulation. Vector signal generators are also capable of generating waveforms and modulating those into your signal. So you can see just some of the basic waveforms: sine, square, ramp, and then was that a sawtooth wave? So that you basically can do complex signals using IQ modulation and modulating that onto your standard carrier wave of usually high frequency, around 20, 40 gigs. And so one of the big differences between the analog and the function generator, with an analog, you're able to manipulate the amplitudes of your signals, but with the digital function, yeah, with the digital, you're able digital VSG, you're able to manipulate not only the amplitude, well, and you're also able to the phase of your signal. So you're able to change two different characteristics of your signal as opposed to one. So you get more data to work with there. So you're able to encode more data into your communication stream, depending on your application. And then obviously with that comes the signal manipulation. You're able to manipulate your incoming signals however you want to create the extremely complex signals that we see in most modern communication schemes and even radar to some degree. So as I said, there's the different types of modulations that a vector signal generator can do. So we have the standards, amplitude, frequency, phase. We could also do the arbitrary waveform modulation, as we're able to put in complex signals into our IQ streams. We're able to do some communication protocols, QAM. I know on our vector signal generator we have QAM built in. I don't recall how high it goes up to, but it goes. I know it starts at QAM 6, I believe. Yeah, 6 to, and I believe it goes up to 256. The data sheet will actually mention that, and we can show that to you later. We have pulse modulation as well as pulse chirped. We'll see that later when I mimic or just do a standard radar pulse, and we'll show that on our actual in-lab spectrum analyzer. And one of the features of the vector signal generator is the ability to do additive white Gaussian noise, and we'll also show that in the video later on, where you're able to add noise to mimic real-world noise and environmental issues for simulation, so you can see how your radar receivers and systems handle noise and if they're able to filter them out properly. And so you're able to do a wide array of different simulation strategies. And then obviously the avionics modulations with the ILS systems and how a plane is oriented, and it's real time knowledge of how close it is to the ground, its orientation, its one wing dipping, things like that. So you're able to do a wide array of different modulations for different applications, not just radar simulation.
Edgar, I just want to address a couple questions that came in during the first couple of slides. I did see a gentleman ask, can a vector signal generator be used for both analog and digital signals?
Yes, so a vector signal generator is capable of generating both digital and analog signals. So that's another benefit over a standard signal generator.
Okay. And then another gentleman, I'll take this one, just asked, some general pricing questions. So I just want to reiterate, if you are in the Americas and you need pricing, you could email us at rfsales@berkeleynucleonics.com. And if you're outside of the Americas, please do reach out to Anapico directly, and their email address is sales@anapico.com. These VSGs are vector signal generators. It's our 875 series. We offer 4, 6, 12, 20, and 40 gigahertz options, and then 1, 2, and 4 channels for each of those, along with a plethora of options like low noise, fast switching, internal modulations, things of that nature. You could look at it all on the site, but to address the question, the 4 gig starts around 30K, and then can go all the way up for a 4 channel 40 gigahertz unit. You're looking at almost 300K. So pretty wide range of options, capabilities, and frequency ranges, and pricing as well. So thank you for those 2 questions. We'll save the rest of the questions for the end, but I thought those 2 were kind of some bookkeeping and relevant to what you're talking about. So pass it back to you, Edgar.
All right, thank you. So I know this webinar focuses mainly on radar simulation, but vector signal generators are capable of being used in a wide array of applications. Wireless communication obviously being one of the major factors for a vector signal generator, given the different communication schemes and modulation schemes used in digital communication. Wireless testing, obviously, you want to test how well your receiver is going to um, respond to noise and environmental um, radiation, such as a cell phone next to your Wi-Fi router. Like, yeah, how do you know how it's actually going to react? Is it going to drop signal? So, because I know like, wireless Wi-Fi signals are usually at 2.4, 5, and now 7 gigahertz. So you're able to test the different or simulate different effects on your system using a VSG to test out the different aspects of your wireless communication systems. Automotive testing, same concept. You have a lot of control signals and communication going on within a car. Cars, essentially, these days are computers um, with an engine inside of them. So, like if you think of it, electronic cars these days with auto drive, the amount of information and communications happening within the computer systems of that alone, any type of hiccup would be bad. So you need to be able to test all the systems and make sure they're all talking to each other correctly and they can handle any noise or any problem that may arise before you actually go to manufacturing, as that can be life threatening if a problem occurs on the road. Electronic warfare kind of goes hand in hand with radar simulation. Um, are we, yeah, are we able to counteract signals to stop our radar from detecting a missile or a stealth, or a non-stealth fighter or bomber? Are we able to block communications on the ground? Um, where enemy locations at. So a lot of what the VSG can do is use in electronic warfare, as we use very high signals and complex modulations and signals to deal with the real world applications in warfare. And then radar simulation, obviously, was what we're focusing on more in this webinar, and we'll show you some more on radar simulation and how the signal is produced in our actual 875 vector signal generator later on in this webinar. So the advantages of using a VSG and radar simulation is you're able to simulate almost all real world scenarios within a lab or manufacturing facility. You're able to determine how well your systems will react without actually going out and testing it in $1 billion airplane before knowing exactly how your system is going to work. So, imagine releasing one of our fighter jets with a radar system that hasn't been tested and it fails, mid-flight. So that could cost us billions of dollars as well as the life of a pilot. So the advantages of simulating is, it's more cost effective as well. The portability of it, because these things, the single channel vector signal generators is fairly small. It's benchtop, so you can, move that around to different labs. It's less demanding because you're doing simulations in a closed environment. There isn't a need for massive simulation labs that have all, that try to simulate real world environments. The customization, I think John mentioned it previously. There's a plethora of options, especially on just specifically our 875, and we can tailor the VSG specifically to your application needs. So if you don't need 40 gigahertz and you only need 12, you can go for there. You need lower noise, fast switching. If you're doing a multi-channel, you need phase coherent switching or phase coherent channels. That's another option. Um, they're also extremely accurate. They're being created mathematically, and you can see in real time. You'll see it in the video where I create the chirp pulse and then I generate the actual signal. You can see on the vector graph or the IQ graph as well as the actual signal that it's generating, and that's all done in real time with a high level of accuracy. So, I mean, some of the challenges in radar simulation, obviously, is I've touched on a little bit. You have extremely high frequency range, 40 gigahertz, 20 gigahertz. Those are fairly high in terms of um, signal generation, and especially when you're doing complex signal generation. So when you're doing extremely complex digital modulations, that's it's kind of hard to do on analog systems. So the VSG handles those. It's what it's designed to handle. Environmental factors as well. I touched on that. So say you have an airplane flying through a thunderstorm. You need to be able to simulate that and know how your systems are going to react to that. If are they going to be able to adequately detect things, or are you going to get anomalous readings, basically making your radar useless? Um, and also, you have the reliability and quality assurance. Like, how do you, if you're doing full scale simulations, like real world simulations with actual mock systems out in the environment, you need to have the reliability. Like, that's a lot of checks you have to follow and make sure everything is going to plan, is being followed to the T. That you're following all specifications and standards. So VSG helps a lot with that, because you're doing a lot of the simulation in a lab with a system that's calibrated and it's accurate. So, and I discussed a little bit. One of the options is the multi-channel. So here you can see our multi-channel unit. It's rack mounted. I believe it's a 2U. And you can see one of the signals that it generated there. It's just a frequency modulated signal. So when you have a multi-channel system, a lot of time you're gonna want the channels to be phase coherent. You're gonna want them to trigger within the same time frame. So if you have one signal triggering, you need to know when the second one is going to trigger, and that needs to be accurate. And especially if you're doing communications that require two signals to be able to determine location, or it's just, you're sending pulses for communication. One of the features that you see on a lot of vector signal generators is the FCP. It's the fast communications port. So specifically on our 875, it allows you to stream IQ data directly into the unit. That's one of the options that we allow. So you're able to change your IQ signals on the fly and directly send them. So whether you had them generated from some mathematical simulation software, or you just had them from a previous simulation, you're able to give them direct. As another feature of just vector signal generators or technology in general, is you're able to upgrade as different communication schemes come out. We're able to include them, as a software update. Sometimes you may need to have a hardware update, but it's essentially future proofs a lot of your systems, where you're able to keep up with current trends and technology as it advances in terms of communications and just the RF world in general. So, how to choose the right VSG for a radar simulation? And I touched on this earlier. It's the specifications of the system, and I believe I have here. Let me look at this. Yeah, so a lot of the it's the same features that we always get asked about. The frequency and its stability and accuracy. Big one is phase noise. Even within just standard signal generators, or RF signal generators, phase noise is a very important specification that a lot of people look at. The power levels you're able to get, and the actual accuracy of those power levels. So when you set it to 10 or 0 dB dBm, it's actually set to around that within the settings, or within the accuracy of the unit itself. So these are a lot of the different things that or specifications that you normally would talk to us about, and we help you choose the right VSG for your application. Um, and a lot of we do get a lot of questions about how to connect a VSG or signal generator into your system. So you have a very large testing system, and you want to be able to integrate a unit into your system. So how well the software and the remote communications work is also it's a very large factor, considering these units tend to a lot of the times will go into manufacturing systems. So they're integrated into a massive complex system, and they need to be able to be easily interfaced with the rest of the other instrumentation via software. And so you compare the different models of the VSGs, and we find which one's right for you and your particular application. Tech support is also a very large concern for a lot of companies. They want to know that if something goes wrong with their system, if it's not integrating correctly, or you're having issues integrating it into your software, you're able to talk to an engineer and try to figure out a solution and get it all worked out relatively quickly. You don't have to wait a month to get, to talk to one of our engineers. We're always here. We're waiting, for your questions. We love hearing about your guys' applications, and any problems you have, just let us know and we'll get to them to the best of our ability. So, best practices of radar simulation using VSG. From my research, there really wasn't a best practice overall. It very much depends on the level of which you're using the VSG for simulation. As John touched on earlier, we have the full scale simulation. We have laboratory simulation and hardware in the loop simulation. So it depends on there's different types of simulation you'll be doing, and depending on what part of the manufacturing or development process you're actually in. So a lot of it will start with the laboratory experimentation where you're testing out uh, new schemes and just new mathematical equations to see how they'll actually work, and you'll simulate those using the VSG. Once you have your system checked, simulated enough where you're confident it'll work to how you want to work, then you go to the hardware in loop where you're able to test your simulation or your signals with actual real world communications from other systems. So you're integrating it. This is where you're integrating it into your overall computer system or the control system of your product. And once all that, once you do all that in the simulations, you're able to get rid of all the bugs and everything works. Then you'll go to the full scale simulation where you put it all together and you do full scale simulations as a prototype product. Usually, sometimes it is the finished product. But so yeah, those are just different parts of the different, some of the different simulation types. Please let us know like the different practices. Like I said, I couldn't find anything like specifically said these are the best practices. It will vary by lab and company. They all have their different standards, their different procedures and protocols. So if there's anything you guys can think of, please let us know. We're always interested to hear from our customers and learn about your applications and how you're using our equipment. So yeah, I mean, just let us know. Yeah. And then we're gonna have this is a video of our 875 producing a chirped pulse signal as well as it's going to be a multi-tone signal, and then we'll show what the pulse chirp looks like on just briefly on a power sensor. So let me get the video up. There we go. Okay, so this was previously recorded by me, and you'll see my hand movements in here, but I'll do my best to kind of direct you at what I'm doing at the time. So here's our 875 vector signal generator, and you can see just the front screen there. And this is the software on the computer, so you're able to control it through a GUI. And you can see here, it's just this is the standard pulse chirped, and then you see the carrier wave. And it'll zoom in here a second. You'll see the carrier waves at 4 gigahertz. I just did a relatively low frequency so we can see it on our spectrum analyzer. And next I'll show you. Yeah, so there's the pulse chirped. Specifically, what you're going to actually see is going to be a 50% duty cycle. This was we were just doing some filming showing the actual UI, but everything else is correct on how it's working. And then we generate it, and you can see, I'm going to pause this here real quick. You can see the I and Q right there, the top right, and that's been the points that are the vectors that are generated when you give it all the information, and it generates those IQ vectors there for you. And then underneath, you can see the what the pulse will look like as well. And I believe I will actually, I'll point out the IQ, and you can see the different dots. And it's essentially vectors. Yeah. You zoom ahead a little bit. There we go. That's the 50%. Let me back up just a little bit. Yeah. You can see this is the 50% duty cycle. And you can see there's a lot more points now. So, and then I uploaded it to the unit, and that's the standard carrier. And then this is with the pulse chirp modulation. I just did a relatively easy one to see Otherwise, you'll see the normal packet where it's just basically like a mountaintop looking type pulse. I did this so you could see the individual pulses that make up our radar signal. And this is just, the center frequencies at 4 gigahertz. And then I start the chirping 100 kilohertz before and then ended 100 kilohertz after our center frequency. And then here I'm just showing some of the white Gaussian noise generation. So you can see I'm adding some noise and it's increasing the noise floor on the actual signal. So it's, going higher. And I just kind of play around with the different settings on our white Gaussian noise generation. And I'm going to zoom ahead a little bit where I actually introduce noise to the actual frequency of the signal itself, as opposed to just being kind of around it. So I'm giving you an extremely noisy pulse there with a lot of peaks, and the frequencies around the center 4 gigahertz frequency. So it's only, I believe, 10 kilohertz around is what I'm doing. So it's, not that wide of a, I'm not showing it that wide of a range. But yeah, here I'm doing, this is 500 kilohertz, I believe, given our frequency spans 2 megahertz right here. So you can see I'm just adding, different noise, so you can test a variety of noise settings on your signal and see how your receivers or just your end system reacts to the different noise levels. And let me see, let me zoom ahead a little bit. Yeah, and it's just different noise levels. This one I did a lot of noise just to see how it would look. And I believe, next I'm going to do the multi-tone. Let me zoom ahead here. There it is. So that's right here, 7-tone. I just did let me pause it. It's a standard 7-tone signal. It was fairly easy to generate. That's the first time I'd actually generated a multi-tone signal on our 875. So fairly easy to do. And it's just, like I said, I'm just showing some of the capabilities of the unit itself. And let's see, zoom ahead. And then now we're going to show the pulse chirped on one of our peak power detectors. So we'll see it on our standalone power unit. And you can see just a standard pulsed chirped signal. If I were to zoom out, you would see the typical envelope of a radar signal. But yeah, I mean, that's kind of what you expect with what I was showing. So you can see the particular pulses and the power level changes. So I believe, so, and that's the, let me pause here. That's the FCP port on the back of the 875. So if you need fast communications, you need to input your IQ information directly into the unit. That's what you would use. And our unit comes with Ethernet and USB communications.
Edgar, there was just one additional question. How can a vector signal generator be used in development and testing of wireless communication systems?
It's a good question. I think I touched on it a little bit earlier, where you have a Wi-Fi signal, whether it be 2.45 or 7 gigahertz, and you need to know how your receiver or how your system itself is going to react to real world environmental issues. Everybody these days has a cell phone, so having cell phones near not just your receiver but your transmitter can affect a Wi-Fi signal. It affects most signals. I know a lot of you probably sit at your computer, nowadays with the work from home, your cell phone sitting on your desk, you get a text message and all of a sudden you're choppy and distorted to everybody else. So a vector signal generator is able to create your signals, and then you can test them with a wide array of different noise profiles or even slight shifts in the frequency and added signals being relayed on top of your carrier signal, just so you can see how your system's actually going to react to that. So it's actually very important in wireless communications in general, simulate, because there's a lot of radiation, RF, microwave, all that propagating through the air just in general. If we could see it, we wouldn't even be able to see past our my hand here, because we're just constantly surrounded by signals constantly. So you need to know how your system is going to react to that, especially in a house where there's walls, air conditioners, heaters, all those things putting out large EM fields and noise. So
Okay.
vector signal generator is you're able to simulate and kind of prepare for that.
Awesome. Thank you. And then what I'll do is I'll just do a quick recap here, and then we'll get into some of the questions and answers that I saw in our Q&A chat over here to the right. Thank you for providing those. So what we covered here was an introduction to VSGs. Edgar did a great job of going over specific applications, and then he touched on advantages and challenges specifically to radar simulation. So we appreciate that, Edgar. So questions and answers, I do have, I think it's like 3 or 4 that I saw on the side. Constantine, he asked what range of band testing communication systems, what range of band testing. So yeah, asked that twice. So we were just wondering, did you mean Wi-Fi, cellular, etc.? In general, we cover up to 40 gigahertz, covering 3G up to 5G. And then Constantine then asked, can the VSG work in low frequency range? Examples of 10 megahertz to 2.4 gigahertz. Yes, the 875 covers 10 megahertz to 2.4 gigs. Ebenezer asked, what is the IF frequency or IF frequency range of EXA signal analyzer? Thanks for your question, Ebenezer. This is an Agilent unit, and we don't have the exact specs, but we'll email you. Thank you for providing that once we find out. Frank Leonardo asked, what advantage does this have over a standard signal generator modulated by a function generator? Standard signal generators only do analog modulation and is not able to perform the digital modulations. So let us know if there's additional questions on top of that, Frank, but I think that answers that. And then Eamon asked 2 questions. Does the chirp have a recommended range before it loses magnitude flatness? The answer to that is typically 10% of the CW carrier frequency, Eamon. And then
That's pretty much a standard. Like
okay.
Like it's a standard for chirp, yeah.
Thank you. And then he asked, is it possible to correct the chirp flatness? To which we're not sure if we could go above 10%, but John Louder, our CTO and head of engineering, will be testing that with the engineering team, and we will email you an answer, Eamon. So thank you again for that, for participating and for those questions. Those are very thought out. I just want to reiterate, if you are in the Americas, to contact us at info@berkeleynucleonics.com or rfsales@berkeleynucleonics.com. If you are not able to share, the details of your application or specification requirements, we do have NDAs in place with several companies if that's something that's necessary for you to share that. Or if you want to reach out via phone and discuss some of the options or abilities of this unit and how it might relate to what you're doing, we have engineering teams and sales engineers standing by, looking forward to helping you. If you are outside of the Americas, please do contact sales@anapico.com. They are our partner and offer pretty much the exact solutions and service that we are able to provide here in the Americas.
There's also one thing I wanted to say. It's like, I know this was a little, we didn't go that in depth into radar simulation and the other applications. It's kind of difficult to do within a time frame. They're very complex applications. So feel free to directly come to us with questions. If I didn't touch on anything here specifically you wanted to hear in this webinar, feel free to email us and let us know, and we'll, the best of our ability, we'll answer your questions and concerns relating to your specific application. So
thank you. Lastly, I just wanted to touch on our BNC Academy. This is something that we've done for, I think, 3 or 4 years now. We have affiliate programs available. These courses are very engaging with videos, credible source material, and downloadable contents. I know a lot of employers, whether it be in the public or private sector, if you submit this course outline, they have continuing credits options. We do offer certificates, credits, and hard copies of a lot of our courses. I know a lot of universities in academia have implemented this either for extra credit or as part of their curricula. And just lastly, I'll leave this up here for a second, just in case anybody needs to write it down. I do know Berkeley Nucleonics is kind of a mouthful to spell and say. If you have any questions regarding this product, this webinar, our academy, anything that we do, please do reach out. We look forward to hearing from you. We want to thank everybody for spending the time. We know time is pretty valuable these days, and carving out an hour of your busy workday to learn a little about what we do and how we're trying to improve, helping solve some of the problems in your field. We greatly appreciate it. So thank you, Edgar, and thank you all for attending, and we'll see you on the next series, probably in a month.